Morning, everyone. My name is Alexander Brick, and today I'm presenting a recent study titled Multi-Parameter Hemodynamic Monitoring via Machine Learning, a data-driven framework for cardiovascular physiology, which proposes a novel, non-invasive approach to predict systemic vascular resistance, CVR, using machine learning and physiological data. So let's get started. And first of all, let's start from the problematic. System vascular resistance, or CVR, is crucial for understanding cardiovascular load and vascular health, but it's clinically underused because it depends on measuring central venous pressure, which requires catheterization. That makes CVR impractical in outpatient primary care or wearable settings. This limits early detection and personalized therapy. The core idea is simple. Instead of measuring CVP invasively, we learn to infer it from signal we can easily obtain, like heart rate, stroke volume, and blood pressure patterns. With machine learning, we can detect hidden relationships that conventional formulas overlook. This study used a comprehensive cardiovascular dataset including over 30 features per patient, from blood pressure and flow dynamics to wave morphology. CVR was computed using standard clinical formula as a reference. Then we discretized it in three categories to match clinical decision points. Here again, this is our formula for CVR. Okay, we can move forward. For over 30 signals, the final model uses just 5, all non-invasive and clinically interpretable. These features were selected using permutation importance across models, with weight based on classifier accuracy. This approach balances robustness with clinical transparency. Classifiers used. We tested 4 classifiers with different assumptions, from linear to nonlinear, local to global. This allows a fair evaluation of the complexity needed to predict CVR. All models were trained using only 5 selected non-invasive features. Confusion matrices show that the models rarely confuse low and high CVR. They make errors at the class boundaries, like normal versus high. That reflects true clinical ambiguity. Random forest performed best, showing confident prediction across all classes. So we can see random forest on the bottom right corner. Random forest reached near perfect performance with 99.89% accuracy and F1 score. Even the simpler models performed very well, confirming that CVR is indeed predictable for non-invasive data when the right test features are used. Here is the result once again. As we can see, logical regression is have the lowest results, and the random forest have the higher results. The KNN and CVC have average results. In summary, this study presents a robust, interpretable framework for non-invasive CVR prediction using machine learning. It enables accurate classification using just 5 easily measurable parameters, a breakthrough for safer, smarter cardiovascular care. Future directions include wearable deployment, real-time monitoring, and clinical validation. Thank you for your attention.